Greetings and welcome to another Insight Project video. Welcome. So, as you saw in the little lead-in there, that was a Hall effect sensor doing the commutation to spin a pulse motor. And I found I really like these Hall effects for commutation, especially going to an Arduino. But since I'm starting to use them, I thought I might try to learn both for myself and if others want to come along, what exactly are they? Why does it do that? And that's the formal, title for what this first part is, the theory, the why does it do that part. And there is enough, I figured let's divvy it up into two parts. And then part two, we'll go, all right, this wire goes here, this wire goes there. When you're on DigiKey, you don't get that. And then it goes. And that'll be part two. So some people might only be interested in that. What I did here is, instead of just, the normal kind of thing, I just went back to Edwin Hall's paper. There's one paper that gives the eponymous Hall effect. And so we just go over that and suddenly everything's understandable. As we'll see here, you can look at, like Wikipedia. A lot of times it's just like, it's just very complicated and difficult to understand, and then sometimes if you do understand it, occasionally it's just gibberish. But it's, you could just go back to what the man wrote, and 9 times out of 10 that's the best approach. Usually when you do that, things become like twice as understandable immediately and 5 times as interesting, and that was the case here. So we're just going to go over his article, and then we'll know why there's a Hall effect, and what we can expect when we're using a component. And then you start to worry about, well, this one is drawing too many milliamps, or the threshold voltage is wrong. But you have to actually know what the heck is it first. So that's what we're doing. Not to get carried away. Let's get busy. So again, you could try and like look at Wikipedia or another encyclopedia or something. It's not real good. The Hall effect is the production of a potential difference, the Hall voltage across a conductor transverse to the current of the conductor and to an applied magnetic field perpendicular. It was discovered by Edwin Hall. The Hall coefficient is defined as the ratio of the induced electric field to the product of the current density and the applied magnetic field. It is a characteristic of blah, blah, blah. And it gets worse from there. They just immediately jump into Hall effects within voids. All right. Hall effect superposition. The theory was kind of all right. I mean, some of the pictures are good. And then, you get a lot of this is actually good, but there's a lot of, this and this and this, and it's like, well, somebody first just say what the heck's going on. But if we go back to discovery, it was discovered in 1879. Edwin Hall was exploring this. There he is. He's a very serious man, serious mustache. This is the first time I've seen his picture. And he was doing his, he discovered the Hall effect. He's got every right to have that powerful a mustache. Right. Let me look at him once more though. Yeah, you don't want to argue with him. That's my take there. So in any event, there's him at Johns Hopkins, 1879. Wow, that's interesting. That picture must have been pretty, like right around the start of pictures. But, well, that's not it. Here it is. On a new action of the magnet on electric currents. So, I mean, this is the 1879 picture for why there's a Hall effect. So let's just look at, as I said, look at what the man wrote. And again, suddenly things are easy to understand. And it's all very interesting, especially when taken in context. Okay, so let's get started. And this is the paper on a new action of the magnet on electric currents that gave rise to the eponymous Hall effect. We should probably provide some context and get a lay of the land here, which will make this, I think, even more interesting. So this paper was American Journal of Mathematics, September 1879. So right there, we know this is before Rutherford, this is before J.J. Thomson, so this is before any concept of an electron. But it's not before Maxwell. And so Hall was a fellow at Johns Hopkins, and he says he was reading Maxwell's Electricity and Magnetism, and he was attracted by the following passage. And you know, just to give a little more context here, I mean, this is Mr. James Clerk Maxwell to you and I. I mean, this is the guy with the terrifying partial differential equations that nobody understands. At least I can't. I don't know what the heck he's talking about. Maybe I should try harder. But this is one of those rare occasions, I'd say, where someone has something that's pretty darn complicated, but also really useful. Sort of like Newton's Principia Mathematica. You know, how many people understand it, but you know, is anyone going to say it's not good? So this is you know, Maxwell's equations, and the same guy. And so he's saying he's reading this there, and let's see if we can highlight it. It must be, now this is Maxwell, it must be carefully remembered that the mechanical force which urges a conductor carrying a current across the lines of magnetic force acts not on the electric current, but on the conductor which carries it. And then he goes on to say, so if you put a permanent magnet next to a wire with current flowing in it, it's going to move the wire for a bit, but then, you know, once the wires settle down, the distribution of the current will be found to be the same as if no magnetic force were in action. So Edwin goes on to say then, this statement seemed to me to be contrary to the most natural supposition in the case considered. So, you know, this is where I'm kind of saying that things aren't as neat and tidy once you get away from the textbooks. He's not actually saying, well, that sounds stupid to me, but he's sort of saying, yeah, I think that's wrong. Taking into account the fact that a wire not bearing a current is in general not affected by a magnet, and that a wire bearing a current is affected exactly in proportion to the strength of the current. So Edwin's saying, you know, the great and mighty Maxwell, I think, is wrong here, that the magnet doesn't act on the conductor itself, it acts on the current. So when he thought of this, and then he brought it then to, well, first I should say, he also notes that he found this article by Professor Edlund that's saying the same thing, that a magnet acts upon a current and it's not acting upon the conductor. So he's saying that, you know, since these two authorities don't agree, he brought the question to the head of the department, Professor Rowland. And there's like a whole story there with Rowland. You know, one could talk for hours about him as well. He was a very well-known, you know, he's the head of the department there at Johns Hopkins of Engineering, and a very well-known scientist at the time. In fact, and I haven't read much at all of Tesla, okay? But I've seen Tesla comment. This is around the same time when Tesla was doing his things. So I've seen Tesla comment very favorably on Professor Rowland. He's perhaps best known for this very highly skilled technical work relating to making diffraction gradients for very good spectroscopy. So a top-notch experimenter and a top-notch scientist. So now the department head goes on and says, yeah, I think Maxwell's full of it too. All right, he didn't say that. But he said he doubted the truth of Maxwell's statement, and he tried to look into it, but he was busy and he didn't get anywhere. So now he goes on and he came up with a plan, and he figured, well, if it's acting on the current in the conductor, then when you bring a magnet past, there should be a change in the resistance of the conductor. And so he goes on for about a page, exactly how he did this. And, it's very understandable, but then he gets to, unlike some passages in the textbooks, then he gets out to the result of that, and apparently then the magnets cause no change in the resistance of the coil. So that didn't work. But he didn't drop the matter there. And here he's saying if electricity is assumed to be an incomprehensible fluid, so this was like before the electron, it may be the magnet's tending to deflect the current, but it's not really able to do so. So basically, the next thing he tried was he took a strip of metal and put it near a magnet, and then he measured it with the two poles with a sensitive voltmeter, galvanometer, and he couldn't find anything there either. So he goes back to Professor Rolland, said he still couldn't find anything. And Rolland then advises him to repeat the experiment, but this time instead of a strip of metal, use a piece of gold leaf on a plate. And so he did this, and on the 28th of October, ta-da, when he brought a magnet past the gold leaf with the current flowing through it, there was a decided deflection of the voltmeter needle, and it was large enough to not be the magnet acting on the galvanometer or any similar cause. And then he says the effect was reversed if the magnet was reversed. So one pole of the magnet's giving a positive deflection, the other pole of the magnet's giving a negative deflection. You start to see where we're going with this? So now we have a situation where you bring a permanent magnet by a wire with current flowing through it, and you see either a positive or negative current that shows up on a voltmeter. Now, the way it's visualized now, and I don't know if I get a chance, maybe I can try and find some images for it, but the way it's visualized now is that the magnetic field will either pull or push some of the electrons to one side of the wire. So if you figure you have some of the electrons going to one side of the wire, that'll develop a negative, and in sympathy the other side will develop a positive pole. And so you have this positive and negative that develop orthogonal 90 degrees apart from the direction of the current flow, and that's the Hall effect. It's very, very closely related to the Lorentz effect, and I don't know if they had the name for that then, but he's talking about here, perfectly well known that two conductors bearing currents parallel in the same direction are drawn towards each other, and if they're going in the opposite direction, they repel each other. I can't say I've read much of Eric Dollard, the great experimenter and the scientist of our age here, but I do remember, like during one lecture, he's talking about the power grid and him seeing these two big power lines, that it was a hot afternoon and they're running in opposite directions, and they move apart because of the Lorentz effect. So this is very closely related, although this is, you're bringing a magnet in and it's pulling some of the electrons towards it, and so you get a positive on one end of the wire and negative on the other side of the wire, or it's pushing them the other way, and so that's why you get that. I'm not going to go through the whole rest of the article. We'll just see if we can get his summary here. So just to wrap up the paper, he concludes here, is perhaps allowable to, let's see if I can highlight it. No, that's not it. it is perhaps allowable to speak of the actions of the magnet as setting up in the strip of gold leaf a new electromotive force at right angles to the primary electromotive force. And this new electromotive force, under ordinary conditions, cannot, under ordinary conditions, manifest itself. You don't see it, the current in which it might work being incomplete. But when he put in a Thomson galvanometer, a current flows, and he saw that. And the other thing that's useful here is that the stronger the magnet, the more of this right angle electromotive force you see, and the weaker the magnet, or the further away the magnet is, the weaker it is. I guess the very last thing I would just say on this, and then we'll wrap it up and go to the practical stuff, is Rowland was actually, who's the department head at Hopkins, was actually appointed to, recommended to be chair rather, by Maxwell. And you can kind of see the integrity and devotion these people had to science, because there was no politics at all here. I mean, even though Rowland was appointed by Maxwell, you know, he's still, I think you're wrong there, James. And nobody seemed to have any problem with it. And so that is something that I hope is kept in mind, I would have to say returned to in the present time, where there wasn't really any politics or personal feelings involved here. They were all just looking at nature. So you can see when you go back to the source material how much more clear all of this becomes. And so if you take a battery, maybe throw in a resistor, and run the current through some gold leaf to the other end of the battery, and then you take a magnet, and I need to be careful because I think through much of the video I was saying, you know, a magnet comes past or something. This has nothing to do with Faraday type induction. You just take a permanent magnet and it sits there without moving while that current's running through that gold leaf. You take a voltmeter, put one end of the probe on one end of the gold leaf, the other on the other end of the gold leaf, and you get a voltage difference. And if the magnet's north facing, you might see a positive voltage. You flip it over, now it's a negative voltage. So that's the basis for the Hall effect sensor. And you know, at some point you might want to go back and, you know, talk about voids and superposition and all the other equations they were going through on Wikipedia. But you know, first you want to figure out what were they talking about, and this is actually what they were talking about. And this is you know, very simple and understandable and repeatable. And this is why you have Hall effect sensors. So now what we're going to do is do part 2 and, you know, say, well, don't get this off a DigiKey unless you're trying to do that. And, you know, once you put this bar here, this bar there, then you're good to go, and everything works. And so we'll have some fun. You know, we'll maybe spin something or light some LEDs with it just to show this in action. Yeah. Okay, thanks everyone. Stay healthy.